Well, here is unit number 2, Forces and Newton's Laws. Lesson A, we're going to deal with Newton's first law. Throughout this unit, we're focusing on standard number 3. Students will understand that Newton's laws of motion predict the motion of most objects, and that those laws can be used to calculate the effects of forces on the motion of objects. Our targets for today, for lesson A, will be to understand the historical basis for Newton's first law of motion, explain the meaning of the physical property of inertia, forces, net force, and equilibrium, and understand Newton's first law of motion and be able to use it to explain the behavior of objects. So say some 2,000 years ago, ancient Greek scientists were pretty familiar with some of the ideas that we have that we study in physics today. But one thing that they were kind of confused about was motion. One of the first people to study motion seriously was Aristotle here. In Aristotle's view, motion was divided into two types. He called it natural motion and violent motion. His idea of natural motion was that all objects are made up primarily of like earth, air, fire, or water. And when things are in motion, they're striving to get back to their natural place. So like a ball of clay being made up of mostly earth would fall to the earth, and a feather being made up of part air and part earth would fall to the earth, but more slowly than the ball of clay. Then he also talked about violent motion, and his idea of violent motion was that things would move because of some sort of force. So basically, Aristotle taught that all motions are due to the nature of the moving object or due to a sustained push or pull. And he said that provided that an object is in its proper place, it will not move unless subjected to a force. So in Aristotle's view, the normal state of an object is to be at rest. Now, if we fast forward about 1,500 years, we come to this guy named Copernicus. And Copernicus was the first person to say that the Earth was not the center of the universe, that he was the first to propose the idea of a moving Earth. Prior to this, it was believed that the Earth was stationary and that the Sun and all the other planets and stars moved around the Earth. So Copernicus was the first to propose the idea of a moving Earth. Now, into that came Galileo. And it was Galileo who proved this Copernican view of a moving Earth. So he accomplished this by discrediting the Aristotelian ideas about motion. Although he was not the first to point out difficulties in Aristotle's views, Galileo was the first to provide conclusive evidence through observation and experiment. So contrary to what Aristotle would say, Galileo found that a stone twice as heavy as another did not fall twice as fast. And he's said to have done this by dropping various objects off the top of the Leaning Tower of Pisa and compared their falls. And it was through this experimentation that Galileo found that objects of various weights, when released together at the same time, fell together and hit the ground at the same time. And of course, we find that to be true when air resistance is removed, different masses will land at the same time. And then it was into this time period, and in fact, it was just a few months after Galileo died, that Newton was born, and he was the one to then fully explain Galileo's ideas and what we now call Newton's 3 laws of motion. Now we'll get to Newton here in a little bit, but let's stay with Galileo for a little bit. Galileo was really important to science in that he was the first person to ever really experiment and find evidence and then report that evidence. Now, whereas Aristotle, he was a really good observer of nature. He dealt with problems around him rather than with abstract cases that did not occur in his environment. motion always involved, for Aristotle, a resistive medium such as air or water. He believed that a vacuum to be impossible, and so he didn't give serious consideration to motion in the absence of some sort of interacting medium like air or water. That's why it was pretty basic to Aristotle that an object required a push or a pull to keep it moving. It was this basic idea that Galileo denied when he stated that if there is no interference with a moving object, it's going to continue moving in a straight line forever. No push or pull or force of any kind is necessary. And where Galileo really was much further along than anybody else of his time was that he was tested this hypothesis by experimenting with the motions of various objects on plane surfaces tilted at various degrees, or we call these inclined planes or ramps. So he would move objects around on ramps, and he of course found that when he sloped downward, speed would increase. When he sloped upward, speed would decrease. And if there was no slope, the ball would eventually come to a stop, not because it was its natural nature, but because of friction. Now, this idea was supported by Galileo's observation of motion along smoother surfaces. When there was less friction, the motion of objects persisted for a longer time. The less friction there was, the more the motion approached a constant speed. So he reasoned that in the absence of friction or other opposing forces, a horizontally moving object would continue moving indefinitely. Now, he further experimented by taking his inclined planes and then putting them next to each other. And what he found was that when he released a ball from one point and it went down a plane, it would rise up to that same position on the other side. And even if he inclined that plane slightly less, that second plane, it would still rise up to the same height, which would require it to move further up that ramp, further along, for a further distance along that slope. So what this showed him was that on a lesser slope, the ball would lose its speed more slowly. And the less the upward slope, the more slowly it would lose its speed. So like in the extreme case where there would be no slope at all, like this here, when the plane is horizontal, the ball should not lose any speed. So in the absence of any slowing down forces, the tendency of the ball is to move forever without slowing down. And we call this property of an object to resist changes in motion, inertia. So inertia is a property of matter that resists changes in motion. And what we find is that an object will continue to do whatever it's doing, moving at a constant speed or not moving at all, until something makes it move. So it was Galileo that first came up with this term inertia, which is the property of matter that resists its change in motion. But it was Newton who put it all together into his three laws of motion. So Newton's first law states that an object at rest remains at rest, and an object in motion remains in motion with constant velocity unless it is acted upon by an outside force. So it's also called, Newton's first law is also called the law of inertia. And we can see a few examples of this happening right here. I mean, first we've got this fellow on a motorcycle. He hit the tires. He's in motion. The motorcycle stops motion. He continues in his motion. It's Newton's first law. He's taking a nice little ride through the air there. Then there's three situations here. These we're going to see in class. So here's three questions to think about before coming to class next. Is I've got this coin right here, and I've got a card right there, and a cup here. Will this coin drop into the glass when some force accelerates that card? Here, this is called an inertia ball. Why is it that a slow continual increase in the downward force breaks the string above the ball, but a sudden force increase breaks the lower string? And here, this would be a hammer with a loose head on it. Why does the downward motion and sudden stop of the hammer tighten the hammer head? So I want you to think about those three questions before coming into class to see those demonstrations actually happen. And finally, I got another little picture example of the law of inertia here. This feller was clearly riding along, and he was going to try to be all impressive for his audience here, and hit his front brakes, and he continues on in his motion while the bicycle stops in its motion. So here's a question. A hockey puck sliding along the ice finally comes to rest. How would Aristotle have interpreted this behavior, and how would Galileo and Newton have interpreted it? So before moving on, I want you to pause the video and think about this question for a moment. Now, Aristotle would probably say that the puck slides to a stop because it seeks its proper and natural state, one of rest. Galileo and Newton would probably say that once in motion, the puck is going to continue in that motion, and what prevents that continued motion is not its proper rest state, but the friction that the puck encounters. So this friction is small compared with the friction between the puck and, a wooden floor, which is why the puck slides so much further along in the ice. So changes in motion are produced by a force or a combination of forces. A force, in the simplest sense, is a push or a pull. Here we have somebody pushing a box, and here's somebody pulling a bag. The source of a force can be gravitational, it can be electrical, it can be magnetic, or it can be simply muscular effort. When more than a single force acts on an object, though, we consider what's called the net force. For example, say you and a friend pull in the same direction with equal forces on an object. The forces combine to produce a net force twice as great as your single force. So if each of you pull with equal forces in opposite directions, the net force is 0. The equal but oppositely directed forces cancel each other. One of the forces can be considered to be the negative of the other, and they add algebraically to 0 with the resulting net force of 0. So this figure here shows how forces combine to produce a net force. So if we have two forces of 5n happening in the same direction, we end up with a net force of twice each individual force, or 10 newtons. And if we've got a 5 Newton force one direction and 5 Newton force the other direction, there's a 0 net force. And here if we've got a 10 Newton force in one direction, a 5 Newton force in the other, we end up with a net force of 5 newtons to the right. Now in physics, a lot of the time when we start talking about net force, we write it in a special way. We use what's called it's a capital Greek letter sigma, which means the sum of, and then F for force. So this is the symbol, in symbol form, this is net force. So what I want you to do right now is stop the video for a moment and read in your reading packet, pages 30 and 31, the personal essay before continuing. Okay, so let's imagine we take a 2-pound bag of sugar. We tie a string to it, and we hang it from a hanging scale. So the spring in the scale would stretch until the scale reads 2 pounds. The stretched spring is under a stretching force we call tension. Okay, so tension is a stretching force. So the same scale in, say, our science lab with the tools that we have is calibrated to read the same force as 9 newtons. So 2 pounds in English measurements is 9 newtons in scientific measurement. If we were to hang a bag of sugar twice the size, or twice the mass of this bag of sugar, the English side would read 4 pounds. This would read 18 pounds. Okay, and something to pay attention to on this is that our sugar is under the influence of 2 forces. We have this upward force of 9 newtons that we're calling the tension. Okay, then it's also got this downward force then from Earth pulling it down, and we call that weight. So weight is a force due to the gravitational pull of Earth's gravitational field. So weight is a force due to gravity. We measure weight then in newtons. It's a force. Okay, so kind of the big point here with this bag of sugar is that as it's hanging there, it's in what we call equilibrium. And since it's just hanging there, we know that the net force on it is zero. So what we can say is that something that is in what's called mechanical equilibrium has zero net force on it. Okay, so let's look at another example then of mechanical equilibrium. Right here we have a situation where we've got two painters and they're on a beam that is held up by ropes on either end. Now here the sum of their upward tensions is equal to the sum of their downward weights plus the weight of the beam. So the magnitude of the upward forces equals the magnitude of the downward forces. The net force on the whole system then is equal to zero. So we say that this thing is in mechanical equilibrium. But let's look at this situation a little bit further. So we've got Burl standing alone in the exact middle of his painter's staging, when the left scale reads 500 newtons. So let's fill in the reading on the right scales. So because he's standing directly in the middle of this thing and it's not moving, it's in mechanical equilibrium, we've got to assume then that on this side also reads 500 newtons of force. Now since the sum of the upward tensions then is 1,000 newtons, the total weight of Burl and the scaffold together must also be 1,000 newtons. So if we call the upward tension forces a positive 1,000 newtons, then the downward weights are negative 1,000 newtons. And what happens when you add one positive 1,000 and a negative 1,000? Well, the answer is that it's equals to zero. So we see here that the net force is zero. But let's imagine Burl here decides to move over to this side so that now this scale reads 170 newtons. So if he stands further from the left, what should this scale read on this side? Well, since we know from the first question that the sum of the rope tensions equals 1,000 newtons, and since the left rope has a tension of 170 newtons, then the other rope must have a tension of 1,000 minus that 170, or 830 newtons. So let's say that he's in a silly mood. Burl dangles from the right end of the scaffolding. What should the reading be if there's 0 newtons on this end? Well, the total thing's got to be 1,000 newtons still, so it's got to be 1,000 newtons there. So here's another situation where we have a gymnast hanging from these rings here. If she hangs with her weight evenly divided between the two rings, how would scale readings in both supporting ropes compare with her weight? And then suppose she hangs with slightly more of her weight supported by the left ring. How will the right scale read? So what I want you to do with this is write down your answer on a small piece of paper or something and hand it to me on the watch by date printed on your whisk chart for this video. If you do so, then there will be something for you. Okay, so let's consider objects resting on surfaces. If we've got, say, a book, like on the left-hand side here, sitting on a table, this book pushes down on the table, and the table pushes up on the book with the same amount of force as the downward force of gravity on the book. So the book has what we call a weight force then that is pushing down on the table. The table pushes back upward on the book with this support force that we call a normal force. Okay? That word normal simply means perpendicular. So this normal force is perpendicular to the surface that this book is resting on. Over on the right-hand side here we have a spring. So that if you push down on a spring, the spring is going to push up on your hand with as much force as you exert to push down on the spring. Okay, so it's sometimes a little bit easier to get your head around the idea of the spring pushing back up on you. Well, the table does the same thing for the book. It pushes back up on the book. Just as you stand on the floor, when you stand on the floor, your weight pushes down on the floor pushes back up on you. And we can extend this same thing to standing on a bathroom scale. When you stand on a bathroom scale, two forces act on the scale. One is your downward push on the scale, the result of gravity pulling on you, and the other is the upward support force of the floor. Now, these forces squeeze a mechanism, in effect a spring, inside the scale that's calibrated to show your magnitude of the support force. So it's this support force that shows your weight. When you weigh yourself on a bathroom scale, the support, and when you're at rest, the support force and the force of gravity pulling you down have the same magnitude. So we say that your weight is the force of gravity acting upon you. So strictly speaking, the scale doesn't measure your weight. The scale measures the upward force applied to your body from the scale. So if a 150-pound person stands on the scale, what would be the net force on that bathroom scale? Well, that's in equilibrium. The net force is going to be 0. Okay? The scale reads the support force, which has the same magnitude as the weight. It's not the net force. But say we put two bathroom scales together, okay? And you stand on two bathroom scales with your weight evenly distributed between those two scales. In this case, what would each scale read? Well, if you're standing evenly on each scale, then the reading on each scale is going to be half your weight. The sum of the scale readings will balance your weight, and the net force on you will be 0. If you lean more on one scale than the other, more than half your weight will read on that scale, but less on the other. So they'll still add up to your weight. Like the gymnast in that previous question, hanging by the rings, if one scale reads 2/3 of your weight, the other scale will read 1/3 of your weight. Okay, so things at rest is only one form of equilibrium. An object moving at constant speed in a straight line is also in equilibrium. Equilibrium is just a state of no change. A bowling ball rolling at constant speed in a straight line is in equilibrium until it hits the pins. Whether we're at rest, which we call static equilibrium, or if we're steadily rolling in a straight line path, which we call dynamic equilibrium, in either case, the sum of the forces is 0, okay? And we have equilibrium. So if you think about it, an object that is under the influence of just one force cannot be in equilibrium, which follows from Newton's first law. The net force could not be 0 if there's only one force acting on an object. So only when we have two or more forces can we have equilibrium. So for example, if we have this guy pushing this box along here, if he's got to push it, he's pushing it this direction here. And if he's going to be pushing it at a constant velocity, there's got to be a backwards force from something like friction opposing that motion, so that he has been then pushing it at a constant velocity and is in he's in dynamic equilibrium. Now, back long ago when Copernicus announced the idea of a moving Earth, this concept of inertia was not understood. There was a lot of arguing and debate about whether or not Earth moved. The amount of force required to keep Earth moving was just beyond imagination. Now, they were able to calculate at this time that if Earth were moving, then it would be moving at more than 30 kilometers per second. So the stationary Earth people posed this argument that if Earth were moving, how could this bird possibly drop out of this tree and catch this worm if Earth is moving at 30 kilometers per second? They figured if this bird starts dropping down, well, by the time it reached the ground to get to the worm, that the bird would be many kilometers away from where he began. So they didn't have this concept of inertia to begin with, and so it was very difficult for them to understand the moving Earth. However, since we know about inertia now and we have an understanding of it, it makes total sense then that the bird moving with the Earth when it drops down will continue to move with the Earth because of its inertia. Okay, the same is true as if you flip a coin. You're sitting in an airplane moving along at 700 miles an hour, and you flip a coin up in the air. The coin comes right back down to you. You can walk along and toss a ball up in the air, and it comes right back to you because of inertia. So that'll end Lesson A here. When we come into class, we'll go through and do some demonstrations and activities involving Newton's first law. See you then.